Hello, my name is Nick, and I'm going to talk about some relative entropy comparisons and how these allow us to combine decay rate estimates for quantum open systems to estimate the decay of complex systems or multipartite systems from simpler constituents. So first, I'd like to recall the quantum relative entropy. I think this is familiar to many. It is at the core of quantum information theory. Some recent results have allowed us to derive new kinds of bounds on quantum relative entropy. In particular, if there are matrix order or CP order inequalities between density matrices, then we can use those to imply comparisons between relative entropy. So this particular result sort of takes three densities as inputs and then defines one that looks like a difference that is also turns out to be a density, however. And this gives a comparison that is entirely in terms of relative entropy. This is what we would call a multiplicative bound. There's no extra additive constant terms. So even when these relative entropies are arbitrarily small, this won't reduce simply to positivity of relative entropy. Now, a key result underlying this work is that for several conditional expectations, in this case, we could look at two, ES and DT. If we start with the sum of relative entropies of a density with respect to its conditional expectation, and these conditional expectations restrict to von Neumann subalgebras, they're self-adjoint projectors. This sum is an upper bound on a single relative entropy with respect to a chain or composition of these conditional expectations. And so for a long enough such composition in alternating order, eventually this will turn into a convex combination of a conditional expectation to an intersection subalgebra with another quantum channel. So combined with the relative entropy comparisons, we can derive some new results using this. Now, one of these is an uncertainty-like relation, which relates the entropies of basis restrictions to some constants in terms of the system dimension and the entropy of the original density. Now, this is a fully multiplicative uncertainty relation in the sense that, again, you could actually rewrite this in terms of relative entropies, and even for states nearing complete mixture, it would not reduce to positivity of relative entropy. A broader use of this sort of technique is when looking at what are called quantum markov semigroups, which are continuous time quantum processes given by a Lindblad-Master equation shown here with this Lindbladian generator L. And when we have a quantum Markov semigroup, we would say that it has a modified logarithmic Sobolev inequality with constant lambda if there is this exponential decay of the relative entropy with respect to a fixed point. So for quantum Markov semigroups, if we combine some of these by adding up the generators, it turns out that if a certain relative entropy inequality holds with respect to the fixed point subalgebras, then we can combine the decay rates for the individual Lindbladians to get a decay bound on the joint Lindbladian. So the main application of this in this work is to look at processes given by graph models where we actually have unitaries representing swaps on a given graph and show that we can recover orders that appear optimal, where the optimal orders of the decay rates actually look a lot like the classical constants. So if you want to see more details, there's an archive link, and I'll thank you for listening.